Hi, my name is George Dong, and this is my presentation of Lab 3, which is the magnetic fields of a bar magnet. The purpose of this lab was to observe the relationship between distance and magnitude of the magnetic field, and use the Biot-Savart law to compare distance dependence measurements. So the fundamental principles we needed for this lab was the Biot-Savart law and the distance dependence equation, both of which I have attached snippets of from the lab sheet. And a brief overview of the results, I got n equals negative 2.9399 meters for the slope, and a magnetic dipole value of 3.245 amperes square meters. Here's a capture of my Excel spreadsheet with all the data that I've collected. And from this, it generated a natural log of b sub x versus natural log of r graph with a line with the equation y equals negative 2.9399x minus 14.248. Before I get into any calculations with the data collected, I want to note a few observations. First, the x component of the measured magnetic field increases as the magnetometer gets closer to the magnet. Conversely, the x component of the measured magnetic field decreases as the magnetometer gets farther away from the magnet, which eventually approaches zero. And B Earth has to be subtracted from the y component to get a value for Earth's field. So now I'm going to get into the calculations with the data collected. Just to recall, I have printed the Excel equation that I got again. So y equals negative 2.9399x minus 14.248. Now that negative 2.9399 is the slope, which is represented by n, and that y-intercept of negative 14.248 is the b sub x. And recalling the Biot-Savart equation, which has been linearized to the form of ln of b sub x equals ln k plus n ln of r, you can solve for k, assuming that r equals 1 meter. And so by rearranging that equation and isolating ln of k, you can take the e of both sides of that equation and you get a value of 6.49 times 10 to the negative 7 for k using my values. After finding k, we could find the magnetic moment, denoted by mu, using the equation recalled from the formula sheet of B dipole and axis is approximately mu naught over 4 pi times 2 mu over r cubed. So manipulating this equation to get mu by itself on the left hand side of the equation, we get mu equals 2 times k times pi times r cubed over mu naught. And of course, since we assume r was 1 meter, we can ignore that portion of the numerator. And so plugging in all our values, I got a 3.245 amperes square meters for mu. Now I'll get into my GlowScript model, but first I want to show a couple of excerpts from my actual code. And this part is the formation of the function for the actual magnetic field, which literally was me translating the Biot-Savart law into Python code. And this is how I went about making the observation locations and the arrows to represent the magnetic fields. And the rest of my code can be found in the description of the video. So this is what my model ended up looking like. The orange arrows are the magnetic field on the axis. The cyan arrows represent the magnetic field perpendicular to the axis, and the magenta arrow is the magnetic field 45 degrees from the axis. And because there were a lot of entries on the actual output and I couldn't fit them all into one screenshot, I decided to copy and paste all the entries to the output here. And we're going to pay more attention to the second to last line about to be at 45 degrees at distance d, which I calculated the magnitude of that vector and got 2.865002 times 10 to the negative fifth. And to compare that to the experimental magnitude, we got 3.89611 times 10 to the negative fifth. Now, although the values differ, they're within the same number scale in the sense that they're both times 10 to the negative fifth. So off of that and accounting for human error, I'd say the experiment was quite a success and the values are within acceptable range. So for the post-lab questions, if I didn't orient the phone to compensate for magnetic north, then the initial X component of the magnetic field wouldn't be 0, and that would just throw off the measurements for the rest of the experiment. If I were to stick two identical magnets together, I'd expect the magnitude of the measured magnetic fields to be much higher, probably close to doubling, but not quite exactly doubling.